Example number 3. We have two electrons that are equidistant from point A and also equidistant from point B. And in part A, we're asked to determine the electric potential at A and at B. And then part B is asking for if an electron was released from rest at point B, what would be its speed after a very, very long time? And we'll be using something new in that case. We'll be using conservation of energy. So let's go ahead and start part A. We want to find the electric potential due to 2-point charges. So the electric potential at point A would be equal to KQ1 all over R1. That's the potential due to this first electron, which I'm calling Q1, plus KQ2 all over R2, and that's this charge Q2, this other electron over here. In fact, if you look at these are both identical. So it's really 2K E, which is the charge of electron, all over this distance R, which is 5 centimeters. So let's go ahead and substitute in here. We have 2 times 9 to the power of 9 Newton meter squared per coulomb squared. The charge of electron is negative 1.6 times 10 to the power of negative 19 coulombs, all over this distance of 5 centimeters, so 0.05 meters. So, if you put that on your calculator, you will get negative 5.76 to the power of negative 8 volts. So let's do a similar thing for the potential at B. That would be KQ1 all over R1 plus KQ2 all over R2. So same expression, except now we can pull out a 2 KE all over, we'll just call this R prime, because if you look at point B, again, it's same distance, it's just 13 centimeters. So we have 2 times 9 to the power of 9 Newton meter squared per coulomb squared. We still have negative 1.6 times 10 to the power of negative 19 coulombs, except the distance now is 13 centimeters. So really that is 0.13 meters. So using your calculator, you should get negative 2.215 times 10 to the power of negative 8 volts. So that's question A. Let's go on to part B. Now part B involves the conservation of energy. So what we're looking at is another electron that is placed at point B and released from rest. And what we're trying to find is what is the speed of this electron when it's very far away, so when it goes very far off this page. And so what you need to recall is conservation of energy. If you recall, when the electron is at position B, it has electric potential energy, which is equal to Q times delta V. So at point B, it has this amount of volts, and if we find the potential difference, then we can find the change in electric potential energy, which eventually then gets converted into kinetic energy. So if you look at the top of the page, you'll see basically this statement over here, which is a conservation of energy. The kinetic energy initially, which is it's at rest, so that's 0, plus the electric potential energy, that's Q times V. So this you can think of as QV, all right, is equal to K final, which is 1/2 mv squared, plus Q times V final. Now, if you recall, the final potential is going to be KQ all over R, but if R is infinity, then the final potential will be 0. So let's go back down to the problem, and we're going to write our statement of conservation of energy. That means the kinetic energy initial plus the electric potential energy initial is equal to the kinetic energy final plus the final electric potential energy. You need to write that statement because you're really essentially telling the grader that, hey, I know that energy is being conserved. And be careful when you're doing that, that you should make sure, double check that there are no other forces that are dissipating energy. Maybe there's friction involved, but normally most of our problems basically assume all the kinetic energy and potential is really just kinetic energy and potential energy, and we don't have any dissipative forces such as friction. But if you do, you need to add in work done plus friction in here. Okay, so we can rewrite that as 1/2 mv initial squared, but this starts from rest. So this means this term will be 0 plus the Q times the potential initially, that would be the potential we calculated at point B, equals the final kinetic energy, which is 1/2 mv final squared, and that's what we're looking for, is the final velocity of this electron, plus the final electric potential, which is V at infinity. Now, if you recall what I was saying earlier, V equals KQ all over R. If R approaches infinity, then the electric potential approaches 0. So that means that this term goes to 0. So really what you have is the electric potential energy is being converted into kinetic energy. So we rearrange this equation. The final velocity would be equal to 2 times the charge of the electron times the potential it has at that particular point B, divided by the mass. And we're going to take the square root of all that. So substituting our numbers in, we have 2 times the charge of electron, which is 1.6 to the power of negative 19 coulombs. Actually, technically it's negative, so we should be putting a negative in there. And then we have the negative electric potential, so negative 2.215 to the power of negative 8 joules per coulomb, if you want to think of it that way, divided by the mass of an electron, which is 9.11 to the power of negative 31 kilograms, and it's the square root of all of that. So go ahead and put that on your calculator, and you will get a final velocity, or speed, of 88.2 meters per second. Now technically the direction should be, just by the symmetry of this problem, would be directly away from this this bisector of this triangle here. So right along this line AB, but away from point B. And that's the answer for example number 3.